We can start with one of your papers that's very exciting. So you worked on a paper titled Parallelizing Linear Transformers with the Delta Rule over Sequence Length. Do you want to maybe give us a brief overview of the paper?
This is a so for DataNet, it was not a new model. It was actually published like 4 years ago. And there was a paper called Linear Transformers are Secretly Fast-Rate Programmer. That paper was from Jürgen's team, and they proposed the DataNet, and they built some collection between linear transformers and fast-rate programming. This is like a very classical concept in neural network. It has a long history, and Jürgen has been studying this topic for decades, and they built such a collection, and they also come up with a new variant called DataNet. DataNet was originally proposed in that paper. If I remember correctly, it was a 2021 SML paper. But they do not have any algorithm or any efficient implementation for us to scale it up. And because so they only have a recurrent implementation. And for recurrent implementation, it was quite slow on GPUs because we cannot parallelize it across the sequence length dimension. And in this work, I proposed a new algorithm, a new trunkwise algorithm that I can parallelize the computation of this data raw mechanism across the sequence length dimension. And I can use a lot of matrix multiplication during this process, so I can leverage GPU computational unit like tensor cores.
Awesome. So I think one thing that's really exciting about this paper is you also have a kind of corresponding GitHub that has caught a lot of traction with around 3,100 stars and over 230 forks. Do you want to maybe tell us a little bit about the open source contribution of Flash Linear Attention?
Yeah, I think Flash linear attention, yeah, is a open source library. It is not associated with a single paper. It's associated with multiple paper. For example, like Getty linear attention, Getty DataNet, and there are a bunch of paper. And I integrate all of these implementations in one single library for the community to use it.
Gotcha. Okay, great. So another paper that you have that was in ICML is gated linear attention transformers with hardware efficient training. Do you want to maybe give us a brief overview of this paper?
Yeah, for this paper, so I think in this paper, the first contribution is the proposal of the flash linear attention algorithm for training linear attention. Yeah, I think by that time, people actually don't know how to train linear attention models at scale. I think a lot of implementations they are based on pure recurrence, and like I mentioned before, like if we use the recurrent implementation, we cannot parallelize it across the sequence length, and we cannot leverage GPU's parallelism power, and we cannot leverage tensor cores, stuff like that. So I think in that paper, I take a huge section to discuss about this like hardware principle for optimization and how can we design a algorithm that is better fit the hardware and for training linear attention. And in that paper, we talk a lot about algorithm called trunkwise training algorithm, and I think this algorithm has been the default algorithm for training linear attention model or Mamba2 model.
Great. Do you want to maybe tell us a little bit about the process of coming up with these like the linear attention transformers, and maybe a little bit about how you, like the motivation for the paper and how you first got started?
Yeah. So for this paper, I was inspired by a prior work called RetNet. It was a paper by Microsoft Research, and in that paper they study a linear attention variant called RedLight at scale. And they also mentioned trunk-wise training algorithm, but they didn't have a super fast implementation. And by that time, I want to do some sequence modeling research because I found that in this area there's a bunch of algorithms I can play around with, and I'm interested in system. So by that time, I'm interested in like how to make this red light model fast on GPUs. And then I started learning Triton. It's a GPU programming language developed by OpenAI folks. It was very convenient for algorithm researcher. It's much easier to develop than CUDA. So I spent some time trying to implement RedNet in Triton, and the speed up is very satisfactory. And then I want to not only speed up the model, I also want to improve the model. And I realized, okay, for RedNet, it has a term called the decay factor. And, for irons, a lot of irons have the decay mechanism or the gating mechanism. In the age of STMs, we often call it the gating mechanism. We have the forget gate, and the model can dynamically control how much of the information the model should memorize and how much of the information the model should take as the input. So there are a lot of gating mechanisms. And in RedNet, in that paper, the decay return is a constant factor. It doesn't change across different time steps. And by that time, I thought that should be problematic because if the model can learn when to forget and when to memorize, this could be more powerful right intuitively. And if we have a constant decay factor, it works like a exponential moving average, and when the circumstance is low enough, the previous historical information is definitely gonna be forgotten because we have the fixed decay speed. And imagine you have a decay speed of 0.95, and after 1,000 steps, like the cumulative decay could be zero. So I found this could be very problematic, and I want to reintroduce the gating mechanism. And I also want to make sure that my method could be trained at scale. So I need to be when I design the algorithm, I should make the algorithm hardware aligned, and so I need a lot of consideration. And so I think in that paper I discussed several variants regarding the parameterization of the gating matrix. So we have a gating matrix, and we do element-wise gating to control the memory content. And I think like that paper is also a concurrent work. The gating linear attention work is a concurrent work to Mamba, which is very popular now. And the Mamba one could be imagined as a special case in that framework. And they have a parameterization in Mamba one. They have a parameterization that is less structured, so they cannot write Mamba one into any matrix multiplication form. So Mamba one is not that hardware aligned, and this motivates them to come up with the Mamba 2 follow-up work and trying to make the Mamba 1 model more hardware aligned and to better leverage the GPU computation unit like tensor cores. And in getting the attention paper, I think I make a more holistic discussion about this matter. And I also come up with a mechanism that's sitting between Mamba 1 and Mamba 2. So I'm not sure how familiar you are with the Mamba 1 and Mamba 2 paper. So basically Mamba 1 has a very fine-grained decaying turn. So imagine you have a matrix valued memory, and for each trainer, it has an independent decaying factor. So it's a 4-rank decaying gating matrix. For Mamba 2, the gating matrix has been simplified a lot. So all the channels under the same head. So we also have the multi-head attention mechanism. So for each head, all the channels or the head dimension share the single decay return. And this definitely simplifies things a lot and allow for hardware efficient training. But this decaying mechanism is like too coarse-grained. So yeah, by data, I'm not aware of member two, and I come up with a model that is basically sitting between member one and member two. I can have some sort of fine-grained control over the recurrent memory, and still I can train it using the trunk-wise parallel algorithm. I can still leverage a lot of matrix multiplication. I can train at scale.
Got it. One of the interesting contributions of the paper is that you have two different versions. You have a materialization version with better parallelism but higher memory, then a non-materialization version with more memory efficient. And then one other aspect is that you have this chunkwise parallel form, and so you're basically balancing memory movement against parallelizability. Do you want to maybe talk a little bit about this trade-off?
Yeah, I think like the non-materialization version versus the materialization version is between like it depend on the batch size and the number of head. So on GPUs there are multiple streaming multiprocessor can execute the job in parallel, and if the batch size and the number of head their product is large enough to occupy a lot of streaming multiprocessor, then we are good. We can use the non-materialization version to do it because it has less I/O cost. We do not need to materialize the recurrent hidden state from the shell memory back to the global HBM memory. And in this scenario, we can use the non-materialization version. However, in large-scale training, the batch size tend to be very small. Yeah, and in this scenario, we cannot fully occupy those streaming microprocessor, and we want another dimension for the parallelism. And I think this motivation is pretty much the same as the flash attention to. I think in that work, they come up with a sequence parallelism mechanism. They for each they divide the sequence into multiple blocks based on the query blocks, and each query blocks can run the can do the computation in parallel, and this is the so-called sequence parallelism in the flash attention to paper. And the motivation is also the same when the batch size is small and the number of head dimension is not sufficient to provide enough parallelism. So they want to have some other parallelism from the sequence length dimension, and this was the motivation of the flash attention too. And in our materialized version of the flash linear attention, it shares similar motivation. Basically, we can do the recurrence. First, we only compute the hidden state. We do not compute the output. And in the second stage, since we already have those hidden state for each trunk, and then we can calculate the output of each trunk in parallel. And in this stage, we have a lot of parallelism across different trunk. Yeah, we have additional parallelism from the sequence length dimension, and it is very useful in large-scale training when the batch size is quite small. Yeah.
Gotcha. Okay, that's great. So I think one other paper that you have that's pretty interesting, is you have a paper back from 2023, hierarchically gated recurrent neural network for sequence modeling. I mean, maybe we've already talked about this paper. Do you want to maybe give us a very brief overview of it?
Oh, sure. I think this was a early paper
Mm-hmm.
in scaling up linear arms. Because I first entered the field of sequence modeling with arms in early 2023, and by that time, I think there's a lot of state space model. It's not member. It's the earlier version of the state space model, like S4 structured state space model, and also we have a lot of long convolution model. And I found that okay for this like S4 structured state space model, their decaying speed is is a fixed constant, and I
Mm-hmm.
found that should be very problematic. This is also similar to the motivation of getting linear attention versus red light.
Mm-hmm.
Uh, I think like there's many good technique from the previous R literature, like the making the decay factor data dependent is super useful, and I think this has been verified for a long time. Yeah. I think there is a gap between this linear research and the classical R research. So I want to bridge this gap.
Mm-hmm.
I want to bring back those useful techniques to the linear literature.
Mm-hmm.
And the forget gate is definitely one of the most important component of STM. And I want to bring that forget gate back. So I have this HR, which is basically it's a very simple linear recurrence, except that the forget gate is not a constant value across different time steps. It's now a data dependent value. So for each input, we use a linear projection and also followed by a activation function to compute the forget gate value.
Mm-hmm. Awesome. So I think one thing that's also interesting is you have had as we talked about earlier, a very strong open source contribution towards society, and also seem to be a big believer in open source. You also have a Discord channel as part of the First Linear Attention, um, uh, the Flash Linear Attention community. You want to maybe talk a little bit about creating a good open source community and how you went about doing that?
Yeah, I think I'm the kind of person who want to share a lot of knowledge, and
Mm-hmm.
so like publishing it on archive is a slow process, and
Yeah.
especially if you want to publish it at a conference, there's a long peer review process, and
Mm-hmm.
the information is often not updated,
Mm-hmm.
and the current reviewing system is kind of broken, and
Mm-hmm.
when you attend a conference, you basically you can also you only see those old papers that you
Mm-hmm.
already know like half a year ago. So I found like so for maybe for Discord is a better communication space for researchers to discuss ideas, etc.
Mm-hmm.
And I was kind of inspired by a Discord channel called Elusi AI, and
Mm-hmm.
that was a company committed to open sourcing, and they have a very wonderful Discord channel. And I know a lot of knowledge from that channel.
Mm-hmm.
So I want also do similar thing, but it's more specialized for sequence modeling, for linear attention, for new architectural design.
Mm-hmm.
And then I built up a Flash linear attention Discord channel, and I think there are some discussion happening in that channel, a lot of technical discussion.
Mm-hmm.
I think starting the beginning of this year, I also have a open source seminar called ASAP,
Mm-hmm.
ASAP. It was a seminar. It's fully open, so we so like for each week we invite a speaker to have a remote talk. This seminar is fully virtual because we want the whole world to have access to it.
Mm-hmm.
It's not bounded by the location, and
Mm-hmm.
we upload all the recordings and all the slides to the YouTube channel and
Mm-hmm.
our website, so researchers can have access to it very conveniently. And yeah, so we have this seminar.
Mm-hmm.
Uh, I think to build an open source community is very beneficial. I think like this could make move the field, push the field to move fast, and people
Mm-hmm.
can exchange ideas, and we can researchers can have some agreement between this during this discussion.
Mm-hmm. Awesome. What are your thoughts on, maybe some areas of research that you're interested in the future? So you've already had a lot of really great work in, as we talked about, so this flash linear attention concept. You have had multiple papers on it, as you also mentioned, and it seems like you have this strong interest, as you mentioned earlier, in like the machine learning side of machine learning systems, and like how can we create more efficient algorithms for ML systems. In, the next years of your PhD, are there some specific topics that you're interested in? Like what's next for you?
I think I'm more interested in developing some more expressive model.
Mm-hmm.
Yeah, it's not purely about efficient model. So
Mm-hmm.
I work a lot on efficient sequence modeling, like
Mm-hmm.
linear attention, linear model,
Mm-hmm.
and those are efficient model. But in terms of like the expressivity, in terms of the performance, it's not. It's we can. Our expectation is that we can catch up the performance with the transformers. We are not expecting a linear attention model to outperform transformers by a large margin, right?
Mm-hmm.
And as a machine learning algorithm researcher, I'm more interested in like designing some more expressive model that is like, for example, like theoretically more expressive than transformers, and
Mm-hmm.
it could achieve better performance in those complex tasks like coding,
Mm-hmm.
reasoning, stuff like that.
Mm-hmm.
For example, I think in my recent work, there's a paper called Path Attention,
Mm-hmm.
which is archive paper. I archived in like 3 months ago.
Okay.
In that paper, I come up with a softmax attention mechanism. It's a new softmax attention mechanism. I want to replace the rotary position encoding.
Mm-hmm.
Yeah, because like the rotary position encoding, the rotation matrix is also fixed across different times. That I want I want to use a more expressive matrix to encode this relative position,
Mm-hmm.
and I use the householder matrix. You can
Mm-hmm.
imagine it as a reflector matrix, like elementary reflection. So I change it from the rotation to elementary reflection,
Mm-hmm.
and I make it data dependent. As my previous work, I always want to make these parameters data dependent. I believe in this direction. I believe like all these parameters should be data dependent. We shouldn't fix those hyperparameters ahead. Like in rotary position encoding,
Mm-hmm.
we have a base rotation angle, and we fix it, and we do not learn it during the training. I think this is problematic. And
Mm-hmm.
in the past paper, I come up with a new position encoding scheme
Mm-hmm.
that I have a data-dependent householder reflection matrix to parameterize to model the relative position.
Mm-hmm. Awesome.
And more importantly, I think this is like this we prove this mechanism is theoretically more expressive than rope. So we have some certain there's a theory from theoretical computer science point of view. There's a circuit complexity, and like transformers are within the class of TC0, and
Mm-hmm.
the path attention could be NC1 complete under certain
Mm-hmm.
mild condition.
Mm-hmm.
Yeah, and this is very inspiring. And now we have some theoretical backup. And still we can train at scale, because I also developed some algorithm combining the blockwise algorithm of a householder cumulative product and the blockwise algorithm of flash attention, and combine the two blockwise algorithms into one, so I can train at scale. So in this sense, I make this algorithm hardware aligned. This is also very consistent with my research philosophy. I want to design those algorithms that is scalable. And also it's very principled. I want this algorithm to have some theoretical justification. I want these algorithms to have a lot of like theoretical grounding.
Mm-hmm. That's great. So I think one thing that's really exciting about the paper you just mentioned is that there are a lot of theoretical advantages, like computational complexity, and you basically are showing that path extends transformers beyond the TC0 complexity class, like you just mentioned. Um, I think one thing that's also interesting is that you have this efficient training algorithm, and you have these UT transform representation, blockwise algorithm, and efficient inference. And then you also have this other extension, right? This like path dash FOX. Do you want to maybe talk a little bit about this FOX concept of like forgetting transformer?
Yeah, forgetting transformers conceptually is like very simple.
Mm-hmm.
So,
Yeah.
are you familiar with Alibi?
Mm-hmm.
Yeah, it's a position encoding scheme. Yeah, it's like so forgetting transformers is basically it's a data dependent version of Alibi,
Mm-hmm.
and alibi is also very related to the decaying mechanism or the gating mechanism in the classical R literature. So for alibi, there's an exponential decaying factor in the attention logic computation. So the longer the distance and the larger the penalty, and when you have a softmax operation, this penalty is like exponentially increasing, right? And this is very similar to exponential decay.
Cool. Do you want to talk a?
But in alibi, the decay factor is constant, and for getting transformers, just make the alibi decay factor data dependent. Yeah.
Got it. Do you want
And,
to?
this, and for getting transformers is this. And you can also imagine for getting transformers as the softmax version of Mamba2. So if you remove the softmax operator, you basically got the Mamba2. And for path, if I remove the softmax operator, then I'll obtain delta net, which is like my previous work.
I see.
Yeah, so I think like the delta rule is definitely make a difference. I want to keep pushing this limit, and so I just add the softmax operator back, and I come up with the path. So for path forks, it's basically a combination of the delta rule and this gating mechanism, and so you can imagine that the data dependent version of gated delta net. Gated data is also like a combination of delta net and Mamba2.
Yeah.
I want to collect all of this concept, and I want to build some better model. The intuition is that like for linear attention, we do not have the softmax operator. So this specificity is like it's like bounded, and so researchers often come up with some more advanced, more fancier attention logic computation scheme to improve the performance. When we add the softmax operator back, and the resulting model should be definitely be more expressive, because if we remove the softmax operator from the vanilla softmax attention, we will tell vanilla linear attention, and that method doesn't work at all in linear attention. And we have come up with a lot of techniques like adding the gating mechanism to having the delta rule. And I think now is the time to bring this technique back to softmax attention. So we can use the idea from linear attention to advanced softmax attention. I think this is a very interesting journey.
Awesome. Okay, now that we're getting kind of close to the end, do you want to talk a little bit more generally about, so you talked about some of the interests that you have in the future, some of the research interests. Maybe tell us a little bit about your time at MIT as a student, as a PhD student. How's your advisor, your group, the community there, things like that.
Yeah. Like I said, I'm currently a third-year PhD student, and my advisor is Yong King. Yeah, he's very nice, and he allow a lot of research freedom. Yeah. And yeah, like I can research on any topic I like.
Awesome.
Yeah, I think MIT is in general is a very good community, and inside MIT we have many like seminars and reading groups, trying to put together a bunch of like people with similar research interests. For example, we have the Scale ML seminar, and in this seminar, this is like on-campus seminar, and we have a lot of people interested in scalable algorithm. Yeah, it's like my research interest, and we have a regular weekly meeting in this Scale ML seminar, and we have a lot of interesting discussion and topic. So I think overall MIT is a very good place to do research, definitely.
Yeah, that makes sense. Do you have any advice for other researchers who are interested in ML systems? Either researchers that are in industry that are interested in ML systems, or maybe undergraduates that are considering, pursuing a career in ML systems or getting a PhD? Like, if you were thinking back to yourself in undergrad, now that everything you know from your PhD and your experience working on all of these different libraries, like through Flash Linear Attention, what advice would you give yourself from the past?
I think for undergrad student, is very important to have some solid basic knowledge, you should definitely take your course seriously, like those very classical computer science course like operating system, stuff like that. These courses are very fundamental, and its idea has been used a lot in a lot of MLC's paper.
Mm,
Yeah, so I think for undergrad students, it's very important to learn this basic course very well. And also, I think in general, for undergrad, graduate, or industrial folks,
mm,
if you are interested in like GPU programming, maybe you should definitely check out there's a very great YouTube channel called GPU Mode, and there are a lot of online video teaching you how to program in on GPUs. And I would also definitely recommend the Triton programming language. Without Triton, I cannot even do my research at all. So
mm,
yeah, so all of this my research are based on Triton, and the Triton is really. I think the learning curve for Triton is not that high. Even for undergrad students, I think like if you go through the tutorial, and if you learn the basic concept behind the GPU programming, you should master it in a short period of time. Yeah, it's not Triton is much easier to write than CUDA, Coolers, stuff like that. And yeah, Triton also often bring you often can have a kind of good satisfactory performance for most time. And yeah, if this is sufficient, then it's all good. But if you, maybe for industrial folks, if you want to further optimize this program, then you should learn some other programming language, because Triton is kind of high level programming language. It doesn't give you a lot of control on like share memory, stuff like that. So if you want to control this share memory, to control these registers yourself, you'd better learn some other programming language like colors, Qt, and also NVIDIA recently has a Python DSL called Qt DSL. I heard that that one is great, but also the learning curve is a bit higher than Triton. So I think it kind of depends on the user case, right? Yeah, if you have a strong demand on optimization, you should definitely write coolers, write Qt DSL, stuff like that. But if you just want to have some okay-ish kernel, you can write it in Triton in a short period of time.
mm. Okay, great. Well, thank you for all of the advice. We really, really, really appreciate it. Thanks for taking the time to come on the podcast.
Yeah, thank you for having me.